So differential equations we talked about quickly on Friday, and said that an example could be population, where we know that the rate of change of population over time depends on the current population, some constant times the current population, right? So, and this I said is an example of this is a differential equation. Just like,
What's the difference between a differential equation and a related rate? Or is a related rate just a differential equation?
that's a good question. The equations we were using in related rates were differential equations,
Okay.
relating rates of change. Yeah.
Is
Um,
equal sign equals KB?
yes.
So rectangle square square rectangle. Same deal.
Yeah. This is a differential equation because it is an equation with a derivative. I'm doing something wrong here. I know. I know. Because it's an equation with a derivative in it. Am I even recording now? Other examples. Could be dy dx equals 2x, or d squared y dx squared plus 2 dy dx plus y equals 0. Ooh. Or y double prime squared plus x squared y equals y prime. These are all examples of differential equations. I know, it'll come back. Maybe. I'm starting to think it's a loose wire inside the thing or something.
1, y prime.
Y prime, yeah. I know, it's infuriating, isn't it?
I think you need to. Oh god.
What we're gonna talk about first is solutions to differential equations. For example, well, first a definition. A solution to a differential, I'm going to start writing diff EQ. A diff EQ is a function that satisfies the differential. I said I was going to say diff EQ. The diff EQ. For example, if we have a differential equation that says dy dx equals 2x, a solution to this differential equation would be a function that satisfies this equation, this differential equation. So does anyone know a function for which this differential equation is true? Yeah.
X squared,
Well, but that's not a function.
y equals x squared.
We're not quite done. Although this is one true version. What else could satisfy this?
Plus
Plus
any.
c. And this is what's called a general solution.
So you're just working backwards.
Yeah. Yeah. A more complicated example is if dy dx equals 2y. That's rough. No, it's more complicated than that. It's a derivative that has as a part of it its own original function. What function has itself as a derivative?
Oh,
X,
is it just a
e
constant?
dx.
This is another general solution. If we know, we start with dy dx equals 2x, and we say that y equals 4 when x equals 0. If we're given that information to start with. We said the general solution to this is y equals x squared plus c. But we know that y equals 4 when x equals 0. So we could say that means 4 equals 0 squared plus c, which means 4 equals c, which means y equals x squared plus 4. This is called a particular solution. I want to see how fast this works, if it's worth it.
Snapchat.
I'm Snapchatting it to you, although that wouldn't work very well because you'd have to have photographic memories to be able to use it.
Or we can just
That's going to take a little while. Unless it did that one first. Oh, it did. Where is it? Where does it go?
That's
Hey, look at that.
Would it be, there was another photo called camera photos?
Yeah. Awesome. Cool. So, I'm going to do this, which means this, which gets me this. So, general solution is one that works for. Are you passing notes?
I don't know why it's asking me notes.
Everyone knows about it except me. So a general solution, what's it? Can someone explain general solution versus particular solution?
There's a thing in front of
It's going to come back again in a second, I suspect. See?
That was good.
So general solution versus particular solution.
you should find the
Yeah, a general solution is a family of functions that satisfy the expression, whereas a particular expression, a particular solution, uses what's called an initial condition. This is called an initial condition. Differential equations show up in science all the time, looking at temperature change in a solid that's at a different temperature from its surroundings, for example. Both the temperature change of the solid as a whole and the temperature gradient within the solid, right? Because the center is going to take longer to reach this temperature equilibrium with the outside. And so scientists can develop expressions for the rate of change, which they can then solve to develop an expression for the actual temperature over time, for example. And the reason it's called an initial condition is you might know what the starting temperature of the solid is and what the starting ambient temperature is. And so that's the initial condition. And then as time passes, that initial condition changes. And the initial condition allows you to solve the differential equation and get a particular solution. I'm going to